Information is one of those things that's hard to define in terms of something more basic. It's a way of measuring the number of possible configurations that a system could be in. Or another way to say it is it's a way of measuring how surprised you are upon learning something, right? How much do you learn? So the standard unit of information, of course, is the bit. And a bit is just anything that can be in one of two states, 0 or 1. Or you could say an electron in its ground state or in its excited state. So because of the computer revolution, I think we're now very used to this concept of information as an abstract entity.
The use of information in diverse fields from physics, biology, is it the same entity, or is it a way of measuring, or is it some fundamental aspect that we're looking at?
Well, there is a mathematical definition of information, which was given by Claude Shannon in 1948. Basically, Shannon's definition gives you a way to measure the number of bits, but even in very unusual contexts, right, where you might not think that you could. So, for example, you can measure the number of bits per letter in English text. Okay, and you might think that, well, okay, there are 26 letters in the English alphabet, so that's between 4 and 5 bits. But it's actually somewhat less than that, because English has regularities. The letter E is very, very common. The letter X is not so common, right? And so because of those regularities, there are fewer bits. There's more predictability in English than if it were just a completely random jumble of letters. And it's a very general definition in that you can apply it to DNA, you can apply it to counting the number of states of a black hole, for example. You can apply it to anything, you know, in any field of science.
How about quantum information, which you work in very intensely?
Yeah, so quantum information obeys qualitatively different rules than we're used to from classical information. I mean, many people have heard of, you know, the famous Heisenberg uncertainty principle that says, you know, you can choose to measure a particle's position or you can choose to measure its momentum, but you can't measure both to unlimited accuracy. What this really means is that quantum objects or quantum information has a degree of privacy to it because there's something called the no cloning theorem, closely related to the uncertainty principle, that says if you have, let's say, one electron in a particular state, there is no physical process that can produce a second electron in exactly the same state. You would have to measure both the position and the momentum of the original electron, but you can't do that. And people have actually figured out how to exploit this idea recently, so that in principle you could have quantum money, for example, that would be physically impossible to counterfeit, okay? So a whole field has grown up to sort of just understand how quantum information behaves, how it relates to classical information. Because of the weird rules that it obeys, you know that when you weren't looking at it, you know, it had to be behaving as quantum information.